Kia ora. We're now moving on to our study of fluids. In this video we're going to look at hydrostatics, which is fluids that aren't flowing. So when I say fluids, what exactly do I mean? Well, fluids are basically liquids or gases. So your cup of water is a fluid, and that's kind of the colloquial use of the word fluid as well. But fluids can also just be gases like our atmosphere or a balloon full of air or whatever. So fluids are liquids or gases. So gases are a bit different because they're not sort of held together by intermolecular forces like liquids are. You basically have, in a gas, you have these little particles kind of whizzing around all over the place randomly, and that's what a gas is. All of these little particles moving around, bumping into each other, bumping into the walls of the container, and that is what a gas looks like. So sort of working definition of fluid, apart from being a liquid or a gas, is a kind of a thing that flows, or a thing that will take the shape of the container that holds it. Or a slightly more technical definition is that if you apply a shear stress to a fluid, remember from our elasticity lecture that a shear stress is like when you apply a force kind of that way. If it's a solid, it will kind of spring back afterwards. But a fluid will not resist that, and when you start applying sort of shear stresses to a fluid, the fluid ends up flowing and rubbing against itself. So make a couple of notes there, and they can't resist a shear stress. Right. Okay, now one of the things we need to use quite often when we're working with fluids is the concept of density, and that lets us relate a fluid volume to the mass of the fluid. So for density we have this Greek symbol here which is called rho. It looks like a P but it's got no stalk. So the density of a substance is simply defined to be its mass divided by its volume. And these three equations are just the same equation expressed in three different ways. Now the standard unit for density is kilograms per cubic meter, but if you look up the density of something on the internet, you might find that it's specified either as grams per cubic centimetre or kilograms per litre. Now it turns out that these two are actually the same, but they're not the unit that we want to use. To get to that one, you just multiply by 1,000. And you can, as an exercise, just check using our standard unit conversion techniques just to verify that's the case. Okay, so if we know the density of a fluid, or a solid even, this doesn't just apply to fluids, we can convert between the mass and the volume of that fluid or solid. Okay, so for example, one that you might have come across, e.g. 1 tablespoon of water, which is 15 mils if you're in New Zealand, has mass of 15 grams, but 1 tablespoon of olive oil only has mass of about 14 grams. That's because olive oil is less dense. The tablespoon is a measure of volume. The mass of these things is different because of their densities. That's why olive oil floats on top of apart from the fact that they're a mix, that's why the olive oil floats on top of the water and not the other way around. But we'll get to that later. One that we use often is that water has density of 1,000 kilograms per cubic meter, or 1 kilogram per litre if you like. Okay, so that's density. Another concept that we're going to use all the time is that of pressure. So pressure is just defined to be a force per unit area, very much like stresses as we were dealing with in our elasticity. So stresses are kind of a pressure. Basically when a force is being applied over an area, then we call that a pressure. And just like with stresses, the unit is newtons per square metre or pascals, and pressures are more commonly specified as pascals. 1 pascal is just 1 newton per metre squared. They're equivalent units. So for example, a student has a mass of 83 kilograms, sneakers have total surface area of 0.0290 square metres. How much pressure does the student exert on the ground? Well, this would just be pressure, will be the force. So the force is going to be a weight force, so it'll be mg divided by the area through the sneakers, and so it's going to be 83 times 9.8 divided by 0.0290, which will be around about 28,000 pascals, or we often, because pressure numbers are usually quite large, we often write them down as kilopascals, but the one we use for a calculation is pascals. And you can see that because the area is on the bottom, if we make the area smaller, like imagine that the student was wearing stilettos instead of sneakers, this area is going to become a much smaller number, which means the pressure is going to be much higher because it's the whole weight force coming through a small stiletto. You'd rather be stood on by the student wearing the sneakers than the student wearing a pair of stilettos through the heel. All right, so that's kind of our working definition of what the quantity of pressure is, but in terms of how we experience it, we need to go a little bit deeper. So one thing that you may or may not be aware of is that we have atmospheric pressure, and maybe if you've watched a weather forecast, you've seen all these pressure isobars, these lines that surround the country and they move around with the wind and that kind of thing. That's because basically the atmosphere exerts a constant amount of pressure on everything in it. So here's Carrots here, and Carrots is experiencing sort of a bombardment of air particles all the time from all sides. And there's actually, you might be surprised at exactly how much this is. So this pressure, as far as atmospheric pressure goes, is just due to these random movements of air particles all the time smacking into a surface, and the net effect of those is to put a whole lot of force on it. The reason we don't really feel this is because it's coming equally from both sides, and our insides are at pressure as well, and so we kind of are at an equilibrium. We don't notice the extent of this, but actually it's quite a large amount. So 1 atmosphere is defined to be 101,000 approximately pascals, and that is approximately the pressure that the atmosphere is always at, which is kind of crazy. What does that mean? Well, we can kind of figure this value out by doing a pressure balance. So the Earth, let's just do a little bit of a thought experiment. If you look at the entire Earth's atmosphere, the Earth, turns out, has 5.15 times 10 to the 18 kilograms of atmosphere. Okay, quite a bit. Obviously that atmosphere is not floating off into space. It's because gravity is keeping it down. Okay, so that means there's a net downwards force, or force towards the center of the Earth from gravity, that's pulling the atmosphere in. But we know from our study of forces that there must be some kind of other force that counteracts that in order to keep the atmosphere kind of stable and in equilibrium. And that force comes from the surface of the Earth. So you imagine here's the Earth's surface, like this. These air particles are being sort of drawn towards the ground, but they're also moving randomly, because that's what particles do. And the ones at the surface are going to keep bumping into the surface of the Earth. The Earth is going to be providing an upwards force on those particles as they collide, and then maybe your particle that came down here, then bounced up again, will collide into some other particles and impart some of that upward momentum. And so what it turns out is that the surface of the Earth is exerting a counteracting normal force to balance this weight force of the atmosphere and keep it in equilibrium. So a couple of other facts, and we can figure out how big this force must be. So the radius of the Earth is about 6,371 kilometers. We know that gravity is 9.8 meters per second squared, so we can work out the weight force of the atmosphere. And we also know that the surface area of sphere, let's just put this one up here, is 4 pi times the radius of the sphere squared. So that will give us a way of working out the area of the Earth's surface. So normal force will balance the weight force, so it will have a magnitude of mg, which will be 5.15 times 10 to the 18 times 9.8, and the area, well, that will be 4 pi times 6.371 times 10 to the 6, notice I'm in meters squared, and so the pressure, which is matching this normal force, is equal to that force divided by that area. And do the calculation, and that gives you around about 99,000 pascals, which is very close to our atmospheric pressure that I mentioned just before. So what does that mean? Well, In reality, there's a few other things going on that make the pressure a little bit higher. There's wind and temperature and all that kind of stuff, but we're not going to worry about that at the moment. It's more just to kind of get a sense for where these numbers are coming from. So 99,000 pascals of pressure. Well, how does this manifest? Well, if we have a surface, so let's just say there's a table, and we put on top of the table, say, a meter squared rubber mat. So we've got 1 meter along here, 1 meter along here. What this pressure means is that there's 100,000 newtons per square meter, or around about 10, it's like there's 10,000 kilograms worth of mass pushing down on this mat, which is crazy. There's also that same kind of force underneath the table as well. That's why the table doesn't get crushed and pushed straight into the ground. But if you were to try and, for example, pick this mat up from its center and try and pull upwards, you've essentially got 100,000 pascals or 100,000 newtons worth of pressure trying to counteract you. Because there's no air underneath our mat, it's kind of flush on the table, it's extremely hard to pull that mat upwards. There's effectively 100,000 divided by G, divided by 10,000 kilograms worth of atmospheric weight sitting on top of that mat. So yeah, if you get a chance to try something like that, you know what I mean. Same kind of principle by which a suction cup works. If you stick a suction cup onto the floor, then most of the air is gone. If you stick it onto a smooth, slippery floor, that is. The air inside there has now been pushed out, so there's no pressure pushing the inside of the suction cup. There's just atmospheric pressure pushing it onto the surface, and it's very hard to pull it off directly. You need to sort of prise up an edge of it and let some air in before it easily comes out. Same kind of idea. Okay, so, but like I said, P0, 1 atmosphere is defined to be 101,325 pascals. Obviously the atmospheric pressure any particular day or any particular place is a bit different from that, but this is a sort of a standard value that is referred to as 1 atmosphere. So that's what you get at sea level at 15 degrees when under certain weather conditions or something like that. So that's the idea of atmospheric pressure, which is an example of a pressure from a gas. The particles are whizzing around, smacking into the surfaces, they provide a force on it, and that's what happens. Okay, what about pressure in liquids? Well, these are a bit weird. So let's have a look at an example of a pressure in a liquid. Just to make our life simpler, I'm just going to take a cylinder of liquid that's exposed to the atmosphere. So here it is, kind of full of liquid. Imagine it's brimful. Think of it as a very weird shaped cylindrical swimming pool. So we want to examine the forces on an area of our liquid. So let's just take a slice at this depth. Okay, first off, Pascal's principle is one that we need to know, and we're kind of conceptually used to this idea. This says that if you apply pressure to a fluid, then it's transferred kind of throughout the fluid, as well as onto the walls of the container holding it. So for example, if you are blowing up a balloon, so the air that you're blowing into the balloon is a fluid. Let's draw a little picture of a balloon. Here it goes. Because you're putting extra air particles into the balloon, the pressure is higher because there are more particles whizzing around, crashing onto the walls of the balloon inside than outside. And what Pascal's principle says is that the pressure kind of is transmitted all the way through the balloon, and there's kind of an outwards force being applied to the boundary of the balloon at all points. Same is true of a liquid. If I were to poke a little hole in my fluid here, then water would sort of come out at right angles, squirt out, and then drain away. Okay, so what this means is that if we look at our cylinder of fluid just sort of exposed to the air here, we have atmospheric pressure bearing down on it. Okay, so that's a lot of force pushing down on our fluid just from the atmosphere. Let's also imagine that we have a cross-section area A. So that means the force would be that pressure times the area. So we'll look at forces on slice at a depth of h. So we'll say that this distance here is h. We're going down. So what forces are acting on that? Well, Pascal's principle we'll just look at the downward force actually. There'll be a corresponding normal force upwards because the thing is not actually moving, but Pascal's principle helps us to understand this. So first off, there's going to be the total force will be our force from the atmosphere, so atmospheric pressure times A, that's transmitted all the way through the fluid. If I push down harder on it, the pressure will increase everywhere inside the liquid and on the walls as well. If I press really, really hard, maybe my container will break and everything will go flying out. But as well as that, there's the weight force from the slice above, or from the column above. Okay, how big is that? Well, let's just write this down. P atmosphere times A plus the weight of the column above. Well, that's going to be the mass times G. And the mass is just the density times the volume times G, which in turn is going to be the area times the height to get that volume times G. Okay, now that gives us an expression for our total force at that depth. To turn it into a pressure at that depth, we just need to divide by A. So pressure is force over area, which will be atmospheric pressure plus rho GH without the A. I know I've written the symbols down in a slightly different order, but that's sort of the standard way that this is expressed. So that tells us that our pressure is equal to the atmospheric pressure plus rho times G times H. And this equation is called the hydrostatic equation, and I'll just write it down here. So P equals P surface, okay, it might not necessarily be the atmosphere that we're dealing with here, plus the density of the fluid times G times the height of the fluid. So that's an equation that we're going to make quite a bit of use of in the next little while. Okay, so let's just do an example of using that. So at what depth of water is the pressure 2 atmospheres? So we can see from our equation, so we'll write it down, a pressure at the depth we're interested in is equal to atmospheric pressure, which is going to be 1 atmosphere, plus rho GH, which means that H will be the pressure minus atmospheric pressure divided by rho G. So the pressure we're interested in is 2 atmospheres. So let's just write it in Pascal straight away. So 2 times 101.3 times 10 to the 3 minus atmospheric pressure. This is that same 101.325 number I was talking about before, just we don't necessarily need all those significant figures. Divided by the density of water, 1000, times G, 9.8, which will give me a depth of about 10.3 meters. So if I go 10 meters down, the pressure has increased to double what it is at the surface. And you can feel this. The deeper you dive, the more you feel that pressure sort of pushing in on you, it's particularly in your ears. Okay, the last point that I want to make about pressure is that, and the hydrostatic equation, is that pressure only depends on the height or the depth. So the shape of the fluid does not make any difference. So for example, in this picture here, all of these, any point along this dotted line I'm drawing, will have the fluid at the same pressure, no matter if there's a cone shape of fluid above it or whatever kind of geometry. It literally is only the depth that matters, so we don't need to worry about anything else. We can just use our hydrostatic equation to understand how the pressure works. Okay, so that's why in our equation, the only thing that matters between 2 different pressures, if the fluid is not flowing, is the difference in height. Okay, so that's sort of our very quick introduction to pressure. Next video we're going to look at some ways of measuring it and link it to sort of some understanding about blood pressure and that kind of thing. So we'll call it, give it a break here and continue on soon.